Welcome to this short demo of the software synthesis tool developed by University of Cantabria under FP7 project FPHARAON. We offer a major productivity leap on embedded system software development. We can outline any embedded system application as a set of software components interconnected. Following this approach, we start from a component-based model of our application. Then, and here is where our tool helps, these components need to be mapped into the hardware sources from our embedded platform, for instance an OMAP chip with an ARM processor, GPU and DSP. So, what happens when an application needs to be mapped to different platforms? We can think of two competing families like OMAP and IMX, each of them with its own device evolution. We would like to be able to try our application on both families, but also to migrate to the most modern device within a family. We can make this effortless. The application we are going to try with our tool takes the two images left and right from a stereo camera and extracts a disparity map that is used to obtain a 3D depth map of the whole image. This takes few processing steps like image conversion, rectification, stereo matching and filtering, requiring quite some processing resources. We can see here a component diagram of our 3D imaging application. Each of the yellow boxes is a software component and components are connected through interfaces. The moving green spot illustrates how execution jumps from component to component at runtime. This is a representation of the PIM platform-independent model of the application. Let's have a look at the synthesis process. We start from an application PIM model together with a platform model and a platform-dependent model where components and resources are mapped. First, the tool generates a set of XML files that contain all the model information. From there, the required infrastructure with all system calls is generated. Last, compiler makefiles are also generated. The makefile-driven compilation is run and thus the different executable binaries are obtained, ready to be loaded in our target platform. Please notice that the whole process is seamless and automatic. Now, let's move to the actual tool GUI. We have three tabs that show us the main views of our design. First, the PIM that we saw before. Second, assignment of software components into one or more executables. Third, a platform description showing the cores on our platform, where we map executables to core. This is a console running on our OMAP, where we see the execution of our application as generated by the tool. Now we are going to modify the mapping of the executables. So first we are going to remove the old mapping files, and now we are going to click and drag on this link that is actually assigning the executable to the core. We are moving it from the ARM to the DSP. We save it, and now we continue the process. First thing we do is to generate the XML files. Okay. Here we can see the new XML files generated. Now we generate the infrastructure. This generates a bunch of C code with all the function calls. Okay, and last we generate the make files. You see, here we get the new set of makefiles for compilation. So last thing to do is to actually run the compiler. The compiler is run, binaries are generated, and we can move now to the console where we can test the new binaries. You can see the messages with the DSP calls and initialization, and the actual runtime, as you will see, is significantly shorter than before. As you have seen, the whole process has been very straightforward. So, few messages to finish this presentation. This tool has allowed us to design at a very high abstraction level. Project management is much easier at this level of abstraction. Reusability is greatly improved thanks to the use of platform-independent code. In the same way, parallelism can be tested easily and tried. And we also reduce the need for in-depth knowledge of the hardware platform we are using. That's it. We hope you enjoyed this video and found it interesting. Thanks for watching.